Welcome to the fourth section of this course about graph algorithm. In this section, we will learn about the ways to detect similar nodes and create clusters inside our graph. In this video, we will discover the algorithm implemented in Neo4j and their differences. But first, let me show you a few applications. Why should I want to detect communities in my graph? Well, the idea is to gather nodes with similar behavior. That can be used to understand your graph structure, can also be used for a kind of prediction. For instance, if you can find that nodes A, B, and C are inside the same group, and you know in addition that nodes A and C have a certain property K, you may want to deduce that node B also has this property key. Similarly, you can use this information to predict relationship. If A, B, and C are in the same group, they are more likely to have connections between them. This last information can be used for recommendations, for instance. There are four main algorithms implemented in Neo4j: triangles count, component-based algorithm, the label propagation algorithm, and the Louvain method. As you can see on the pictures here, showing the results of each algorithm on the Karate Club dataset, the detected communities are very different. That's why it's very important to understand what are really doing the algorithm. That will help deciding which algorithm is to be used in which context. Let's start from the triangle count method. As the name suggests, it counts how many triangles formed by a set of three connected relationships pass through a given node. It is insensitive to any relationship direction or weight. In the example here, on the left graph, there are no closed triangles going through A. On the middle graph, only one triangle uses node A as a corner, while on the right graph, three triangles are using the corner A. Let's count the number of triangles in the Karate Club graph. If you remember well from previous section, we have two node labels: person, which represent the original datasets, and some teacher nodes that were added manually for testing purpose. Let's run the algorithm using only the original graph, meaning selecting only the person node label. As you can see, procedure signature is very similar to the centrality ones. The algorithm is returning the node ID, the number of triangles that we will look at for now. The nodes with the higher number of triangles are again nodes 1, 33, and 34, which were also the most important nodes in terms of centrality. But the algorithm is returning another result, a coefficient. Let's order the results by coefficient instead. Here the outcome is different. There are quite a few nodes with a coefficient of 1, and then the values start decreasing. The coefficient is known as a clustering coefficient or transitivity. It measures the probability that a given node neighbors are also connected. If we look at node 17, for instance, which is one of the nodes with a coefficient of 1, we realize that it has only two neighbors, and those neighbors are connected. So the probability for its neighbors to be connected is 1. So the triangle method and clustering coefficient give information about the graph connectivity and can help understand the network structures. Let's now investigate another method, which is called connected component analysis. This method is based on path and gather nodes in the same cluster when there exists at least one path between them. There is a stronger version of this algorithm where a path is required to exist in both directions. How does this algorithm behave on our Karate Club graph? Neo4j retained the name of union find for the weakly connected component algorithm, which we can find here. This algorithm returns a node and a set ID. Let's run this and see what happens. As you can see, all nodes are clustered into the same set. According to the definition, that means that any node in the graph can reach any other node, which is true given the graph structures. By the way, can you think of a method to check this? Yes, you can use the all pairs shortest path algorithm we talked about in section 2, checking that there is no infinite distance. Now, what happens if we run the algorithm on the whole graph, including the teachers? Teachers are nodes completely disconnected from the students, so there is no path from a teacher to a person. That's why now you can see that the teacher's nodes have been gathered together into a different set. All the other nodes, the person one, are still in the same cluster. Let's now move to the next type of algorithm implemented, the label propagation. It's quite new since it was proposed only in 2007. The idea is to assign a label to each node and then propagate this label to the neighbors using the majority vote rules. It's a clustering algorithm less aggressive than the connected components in the sense that it can find different clusters within a connected group. Relationship direction here is important to define propagation. Let's run again this algorithm on our Karate Club graph. The algorithm is called label propagation. We can specify that we want our graph to be considered undirected, and it will return the label of each node. So you can see here, the label propagation algorithm managed to find several clusters into our graph. Last algorithm we are going to describe now is the Louvain algorithm. Its aim is to maximize a quantity called modularity, whose aim is to represent the number of relationships within a group compared to external relationships. To run the Louvain algorithm in Neo4j, we just have to call the Louvain procedure that will return a node and a community label. But let's visualize the result of this different community detection algorithm. So here you can see the result of the Louvain algorithm with and without the teacher nodes. So you can see that when the teachers nodes are included, they are well identified as a separate community. But also, there are several communities identified within the students. To summarize, the triangle method will give you information about the connectivity of your graph. Connected components is mostly related to paths within the graph and will clearly identify disconnected graphs. Label propagation and Louvain algorithm are most suited to find communities inside a connected graph.